the stars. They appear as little more than tiny dots of light scattered across the night sky. But look closer, and what extraordinary secrets are revealed. Stars are vast, blazing spheres of gas that forge the building blocks of everything we know, before finally ending their lives in some of the most powerful and dramatic events in the entire cosmos. The Sky at Night has covered every major space science discovery in more than 60 years of occasionally quirky broadcasting.
It's absolutely tremendous. I'm going to do just a little mathematics. Please don't be frightened.
Now we're going to use that archive to tell the story of the stars and our attempts to unlock their deepest secrets.
Good evening.
Welcome.
Good evening.
Welcome to the Sky at Night Guide to the Stars. For as long as humans have walked the Earth, the stars have fascinated us. And we can trace the beginnings of that obsession back at least 4,000 years, thanks to one very particular ancient artifact. This image shows the Nebra sky disk, a beautiful bronze object about the size of a dinner plate. What's really important are the markings upon it. This represents the crescent moon. This disk has been thought to be either the sun or the full moon, and there's this little collection of 7 stars, which are thought to be the Seven Sisters or Pleiades, a very familiar cluster in the night sky. Looking at it, you might almost miss them, but what we're seeing is something incredibly significant. This is the first known concrete example of an image of the night sky, the start of systematic astronomy. It's been a long journey from the Nebra disk to the present day. And there have been some profound questions to answer along the way. Where do the stars come from? How do they work? And what happens when they die? These are not abstract questions. The answers tell us where we've come from and our ultimate fate. Our first attempts to understand the stars began modestly. Long before scientists discovered what the stars really were, people drew lines between them and gave names to the resulting shapes, the constellations. But it wasn't exactly a precise science.
It's been said, you know, that the sky is a complete picture gallery. Look at this lovely old planisphere drawn in 1730, and there are many mythological figures here. There is Perseus, the gallant hero who killed the Gorgon, Medusa, a hideous woman with snakes instead of hair. And then we have Hercules, who caused such havoc with his 12 labours. Very few constellations in the sky bear any resemblance at all to the objects they're meant to represent. In mythology, Cancer was a crab sent by the goddess Juno to plague the hero Hercules, and Hercules, not unnaturally, trod on it, and that was the end of the crab. Frankly, I find it very difficult to make the outline of a crab out of Cancer or anything else.
Creating constellations brought a sense of order to the apparently random scattering of the stars. It was the first step in understanding their positions and movement, a fundamental skill that's been vital throughout human history. And one star in particular proved its worth more than any other.
I want to talk to you about a very special star. It's by no means outstandingly brilliant, but it is of special significance to us.
We call it Polaris, the pole star, and for centuries, it's been guiding travellers across land and sea.
Why is Polaris so significant? And the answer is that it marks the North Pole of the sky. Just imagine that you're standing at the North Pole. Polaris then is straight above your head. And as the Earth spins, Polaris doesn't move. Everything else seems to go around it. Now, there's another point, too. The apparent altitude of Polaris, that's to say the height above the horizon, tells you your latitude on the Earth's surface. And all through the ages, navigators have found that very useful indeed.
The biggest change in our relationship with the stars came when we went from passively observing them to trying to understand them. And there's one star which is easier to study than any of the others.
We must remember that at the distance of 93 million miles, which is not very far, the Sun is the only star we can study in detail.
It's not surprising then that the sky at night has studied this particular star time and time again.
Tonight, I want to show you a rather unusual film, a film of the Sun in action.
There were many questions to answer, starting with perhaps the simplest of all. What makes a star shine?
There are so many people who believe, and very understandably, that the Sun is burning. But that, in fact, is not the answer, because for one thing, the Sun is too hot to burn. The real answer is entirely different, and we do know what it is, and it lies in what are known as nuclear reactions.
At its core, the pressure and the temperature of the Sun are so high that they cause hydrogen to fuse into helium, releasing the equivalent energy of 4 trillion atomic bombs every second. This energy heats the surrounding plasma, which drives convection currents in the Sun's interior as it rises to the surface. The churning of the hot, electrically charged plasma acts like a dynamo, generating a magnetic field. And where this field pierces the Sun's surface, it can trap patches of plasma, which cool to form distinctive dark spots, sunspots.
I'm not a solar man in any sense of the word, but I've made a good many sketches of the Sun by projection, and let me show you this book. I've never shown you this one before, because it goes back a long, long way. Look at that drawing, which I made with that 3-inch telescope on the 21st of August, 1935.
No, you can't have been more than 12.
I wasn't, but there were plenty of spots to see. Look at that lot.
It's amazing detail. You've done very well with that.
Sunspots are one of the Sun's easiest features to observe, glowing less brightly than the surrounding gas. But they're only comparatively cool. At 3,500 degrees centigrade, if a single sunspot stood alone in the night sky, it would shine 10 times brighter than the full moon. And sunspots aren't the only feature visible on the Sun's surface. The Sun's magnetic field is constantly twisting and reshaping until it becomes so unstable it tangles and snaps, releasing plasma which flies out into space, a solar flare. A fleet of space telescopes monitors the Sun for flare activity, and every so often, we see an eruption more ferocious than anything else in the solar system. A coronal mass ejection.
A typical coronal mass ejection contains about the same energy as about 100 times the entire world's nuclear arsenal.
That sounds pretty scary.
It's an astonishing amount of energy. But a colleague of mine worked out before lunch once that it was also the equivalent to the energy in a Mars bar if it were about 2,000 kilometres long.
These formidable solar storms eject a stream of charged particles that play havoc with any electrical systems in their path. In July 2016, an uncrewed space observatory was temporarily blinded when a coronal mass ejection hit it head-on. If the flare had occurred in the direction of the Earth, it would have knocked out our mobile phone system, our satellites, and even our television. Flares of this magnitude are rare, but smaller gusts of particles reach Earth all the time. We call this the solar wind.
Luckily for us, we have a natural shield against these damaging particles coming from the Sun, in the solar wind and the eruptions, and it's our magnetic field. So similar in shape to the one created around this bar magnet, molten iron within the Earth creates a vast magnetic bubble extending thousands of miles above our heads.
When the cloud of charged particles reaches us from the Sun, it slams into the Earth's magnetic field, and if conditions are right, charged particles race down the field lines. They reach the top of our atmosphere and excite the oxygen and nitrogen atoms, causing them to glow and creating mesmerizing aurorae, a faint trace of the sun's remarkable power. It's rare to see the aurora from the UK, and so in 2017, the Sky at Night went to Norway to discover the latest aurora science.
So we've been driving around for about half an hour now, and I'm beginning to see what might be the Northern Lights. It's quite hard to describe, but there's that sort of a wispy light in the sky, and I'm really hoping that's it, so we can hopefully pull over and check it out. Wow. It really is them. A band of colour across the sky. This is amazing. Anything that usually gets between me and the stars is a bad thing, but at the moment this is just so glorious. It's so much better than I thought. So much more dynamic, so much more colour. I can actually see a sheet travelling across the sky. It turns out that they're not as well understood as you might imagine. Aurora expert Melanie Windridge explains.
Firstly, we know that if charged particles were coming in directly from the solar wind and hitting into our atmosphere, they'd be hitting us on the day side of the planet. And we don't see aurora there. It's too light. Yes. We see aurora at night. Yes. So somehow the particles are getting round to the back of the planet.
New research has begun to suggest an answer. The electrons coming from the solar wind are receiving an unexpected boost in energy.
You get a lot of magnetic field built up and pushing down behind the Earth. And eventually these magnetic field lines get so close, but magnetic field lines can't cross, and so that's when they get pushed close, and then bang, they snap. And when they snap, they catapult back towards the Earth, and they catapult particles, electrons, down the field lines into the Earth's atmosphere at the poles. And that's what's causing the aurora. It's that acceleration of particles. It's giving them a lot of energy, and that means that they can interact with our atmosphere and cause the bright lights that we see in the night side.
Over the last 60 years, we've made impressive advances in understanding our home star. There's one last piece of the sun that's still mysterious. Its outermost layer, the corona, a hot envelope of gas that extends around the main disk. It's normally hidden by the glare of the sun, but there's one spectacular exception. A solar eclipse.
And there's totality, the diamond ring, and there the lovely corona. This is incredible, the best corona I think I've ever seen in my life.
In 2015, Lucy Green explained why the corona is such a mystery.
The corona is hot. Now that might not be so surprising to hear. The trouble is, it's too hot. The atmosphere is a blistering 1 million degrees hotter than the surface.
It's a puzzle because the source of heat in the sun is the thermonuclear reactions in its core. As you move further away from that central furnace, the temperature should go down. Just as the further away you sit from a fire, the cooler it is. But the corona breaks that rule.
The superheated corona really was a shocking discovery, and it's still a puzzle that we're grappling with today. Now, the only explanation is that the corona must be getting extra energy. The question is, from where?
There is a prime suspect. Solar flares. That ferocious release of energy heats the corona.
But there's a problem. Flares, as large and powerful as they are not frequent enough to keep the plasma of the corona heated constantly to its 1 million degree temperature.
Yet flares could still be the answer that may help explain why the corona is so hot. nanoflares, very similar to the big solar flares I study, only 1 billion times less energetic. But although they're small, it's thought they're happening all the time. The nanoflares should give out a faint signal in X-rays. The trouble is that in normal conditions, that signal is drowned out in the glare of the sun's activity. But in the next few years, the sun will move into a period of lower activity, a solar minimum. When that happens, the plan is to point a satellite called New Star at the sun. New Star has a very sensitive X-ray detector, and with the sun in its quiet period, it might just be able to detect the emissions given off by the nanoflares.
If New Star does detect that faint X-ray glow coming from nanoflares and crucially tells us how common they are, it will be a huge step forward in finally solving the long-standing mystery of why the sun has a corona that is so hot.
Observing the sun has taught us a huge amount about how stars work. But our sun is just one star, and a rather average one at that.
We've got to remember always that our solar system is a very small part of the universe as a whole.
There are 100 billion galaxies out there, each with 100 billion stars. If we're going to understand them properly, then we're going to have to venture out into the cosmos.
If you look up into the sky on any dark night, you will see thousands of stars, and all these stars are suns in their own right.
To a casual observer, the stars might all look the same.
Well, I can assure you that they don't. And if you look closely, you can see that they are very different from each other.
The simplest difference between the stars is perhaps a little surprising. Colour. Jen, we're here to talk about colour in the night sky, and that's odd because people think of the nighttime world as black and white.
Yeah, so if we look up at the stars, and we can see some stars here tonight, you think of stars being kind of these white pinpricks of light. You don't think of much colour being out there. But actually every star in the night sky has its own colour, and the classic example I think at this time of year are some of the stars in the constellation of Orion. So the classic stars you want to look for are Betelgeuse, his top left as we look at shoulder or armpit. The other one that you want to look out for is Rigel, which is his bottom right foot as we look at it. And if you look closely at those stars, you'll see that Betelgeuse looks a kind of orangey reddish colour, whereas Rigel, it looks white to us, but it's actually more kind of whitey blue.
So why is that? Why are those two stars different colours?
And this is all to do with their temperatures, and it's a little bit confusing to start off with because it's actually because Betelgeuse is cooler than Rigel. So we've got an example here. This could be my star. So we're going to start lighting up this light bulb, and what's happening is we're going to make the wire inside glow, and you can see here it's kind of glowing an orangey colour.
Right.
As we increase the power through it and we make it heat up even further, you can see the colour starting to change through to a kind of yellow, and if we kept going, I don't want to do that, it will get a little bit too hot, but it will end up glowing very white basically.
And so just by looking at the colour of the light bulb, I can work out the temperature of the filament.
Yeah, exactly.
And the same is true with the stars. Because they're different temperatures, we get these different colours.
Exactly. And so when we look at Betelgeuse, we're looking at a star where the surface temperature is around about 3,500 degrees for Betelgeuse compared to about 11,000 degrees for Rigel. So you've got a big difference.
The more scientists studied the stars, the more they realised that they fit into distinct groups, lining up rather neatly on a graph.
Let's take all the stars in the galaxy and sort of plot them up. One way to do it is you have this axis as temperature increasing to the left, and vertically you have luminosity increasing upwards. When you do that, we find that 90% of all stars align on a kind of a main sequence from the upper left down to the lower right. We call this the main sequence, and it contains stars that are large, hot, and blue in the upper left, all the way down through white, yellow, orange, and red, small, cooler stars. The smaller and cooler a main sequence star is, the dimmer and redder it appears.
But how small can a star get before it stops being a star? The answer was revealed by an entirely new class of object, but one that's incredibly hard to find.
Brown dwarfs are a new addition to our star chart and are the coolest and dimmest of stars. Part of the difficulty has been seeing them because they don't shine brightly like our star. To find them, we need infrared telescopes, which can pick out cool objects. Ben Birmingham from the University of Hertfordshire is a brown dwarf hunter. He uses telescopes like Spitzer and WISE to look for these elusive beasts of the star family, which lurk in the cold, dark parts of space.
They're very peculiar objects. I'm sort of struggling to conceptualise where they sit. They seem a bit like sort of the missing link in between stars and planets somehow.
They certainly are the missing link between stars and planets. The warmer ones look a lot like stars. They show a lot of the behaviour we see stars having. But then the lowest mass ones look like planets. They have weather, for example. You see dust cloud weather and things at sort of about 1,000 degrees centigrade. So you go from studying the kind of the plasma physics of charged particles in a stellar atmosphere with protons and electrons flying around to atmospheric chemistry, where you're using the language of planetary science rather than stellar physics.
And what kind of temperatures are we talking about here?
Well, they range from the temperatures of the coolest stars at about 1,700 degrees centigrade to much, much lower temperatures. And the WISE mission, a satellite from NASA, has managed to push the temperature limit down to about 300 Kelvin, which is room temperature.
So hang on, room temperature, like this temperature?
A bit warmer than this temperature, I think. but yeah, about 300 Kelvin, 20 degrees centigrade.
So how do you say whether something is a star or whether something is a planet?
Well, that's tricky. So people tend to take a kind of gut feeling approach. The definition officially is when something's low enough mass that it doesn't burn something called deuterium in the core when it's very young.
Heavy hydrogen.
Heavy hydrogen, yeah. Whether it burns that in the core when it's very young, then we call it a planet if it's orbiting a star. They have atmospheres that are predominantly composed of hydrogen, but the molecules we see in the atmospheres are things like water, methane, and at the coldest temperatures, ammonia. And it's probable that when we get to these temperatures, we'll start to see water clouds in their atmospheres.
Where are the nearest brown dwarfs? How close are they to us?
Well, they're very close. In fact, just recently, an American astronomer working on his own, looking through the WISE data set, found a brown dwarf within 6 light years of Earth, which makes it one of the closest objects to the Sun.
What, the third closest stellar system, something like that? And we had no idea it was there?
No idea at all. It was hiding against the very crowded background of the galactic plane. Lots of people have been looking, but it's a very hard job to find these things, and a lot of people were kicking themselves.
Yeah, it seems slightly careless to have missed a star-like object that close.
Careless is a strong word.
All right, sorry, I don't mean to be rude, just I guess it tells us how little we know about the galaxy.
Yeah.
So is that the closest one?
That's very hard to say. Probably not. I would say if we're still finding things at 6 light years, there may be things even closer. It would be pretty ambitious to say that's definitely the closest one.
The other odd thing about these stars is that they don't seem to die. They just get colder and colder. They are immortal stars, ending their lives in the lonely emptiness of space.
Once astronomers knew that there were different types of star, they wanted to know what caused these differences. And that meant working out what the stars were made of.
Way back in 1830, a famous philosopher named Auguste Comte cited as one thing that would be permanently impossible a knowledge of the chemistry of the stars. And he said that man would never be able to find out what the stars are made of. Now, when a great philosopher makes a serious, profound, and dogmatic statement, he is almost certainly wrong. And Comte was very wrong because he didn't know about the spectroscope. Now, just as a telescope collects light, so the spectroscope splits it up. And you can spread out the light of the sun and the stars into what's known as a spectrum. What we ordinarily call white light is by no means so simple as it might appear. It's made up really of various colours.
Spectra held the key to finally learning what the stars were made of. You just had to know how to read them.
There was one of these on Mr. Dwyer's laboratory wall at school. Yeah. I mean, they're very decorative, but what do they tell us? This is the sun, right?
So this is a representation of the light from the sun split out into its rainbow, its spectrum of colours. But there are specific colours that appear much darker, and that's because those colours are absorbed by specific elements in the sun's atmosphere. So this one in the red end of the spectrum is absorbed by hydrogen in the sun's atmosphere. And there are other elements as well. We can see that there's small amounts of calcium in the sun's atmosphere and the small amounts of iron in the sun's atmosphere. We can start to get a spectral fingerprint of what the sun is made of.
And the chart above, now this is from a blue giant star. Some of the lines are in a similar position, but there's a lot that's different about it.
The first thing about the blue giant star is that it's very bright in the blue, but it's very dim in the red. And that's because the star is much hotter. The fact that the star's a lot hotter also means that some of those elements in the atmosphere are completely stripped of their electrons already. So we don't see absorption lines, as these are called, from iron and from calcium and that kind of thing. We mainly just see hydrogen in the atmospheres of those stars. And we had the sun on the hot blue stars, and then we had cold red stars. This is one of those cooler red stars. The spectrum's a lot busier. There's an awful lot more lines in there. And whereas the atmospheres of these stars, these warmer stars, are dominated just by atoms in their atmospheres, in cooler stars you can have molecules, you can have chemistry. This is atoms joined together. Molecules absorb light at many, many more colours than just the pure atoms do.
Studying the spectra of the stars revolutionised stellar science, and it even revealed a new element. Helium was discovered in sunlight before it was found here on Earth, and the name helium comes from helios, the Greek word for the sun. Spectroscopy has taken us a long way, but some stars simply defy our attempts to categorise them. And one star in particular is stranger than any other that we've found.
The #1 weirdest star in the Milky Way galaxy. It goes by the name of V Hydra. This star would not otherwise call attention to itself were it not for every 8.5 years, blobs of nearly 10,000 degree plasma come spewing out at 500,000 miles an hour. Then it stops. 8.5 years later, it repeats. Who ordered that? Our best hypothesis is that this giant star has a companion, another star in orbit around it that has a highly elliptical orbit, a highly elongated orbit. Spends a lot of time out far away, but when it comes in close, it comes in real close and punches through the physical body of the red giant itself, pops out the other side, and we think that interaction of a hot star and the red giant is what's responsible for spewing forth these blobs of plasma right on schedule every 8.5 years. So we've never seen this phenomenon before. We think we have the right explanation for it, but it remains a unique object in all the star catalogs that we've accumulated. And for that reason, it is the weirdest star in the Milky Way.
We've discovered a glorious variety of stars, from the entirely mundane to the most far-fetched imaginable. We've made huge leaps in understanding how they work. But there's one big question that we haven't answered. Where exactly are the stars? Star maps can be very accurate, but they can't tell us the whole story because they're necessarily two-dimensional objects. Two stars which are close together on the map could be thousands of light years apart in reality. In order to make a three-dimensional map of the sky, astronomers had to work out how far away the stars are. We finally managed it in 1838 when this chap, Friedrich Bessel, focused his attention on one star, 61 Cygni. 150 years later, Patrick embarked on an unconventional attempt to explain the technique that Bessel used.
Well, you may wonder what we are doing having the sky at night on a cricket field. And this really is a cricket field of Homewood House Preparatory School for Boys at Langton Green near Tunbridge Wells. And we're here for a very special reason. We want to do this programme about the distances of the stars. Well, it's all done by a method known as parallax. I think I better show you really what it's all about. And this is best done by means of a very simple experiment. Will you please close one eye, doesn't matter which one, and then hold up your finger and line your finger up with my nose as you see it in the television screen. Got that all right? Now, without moving anything, use the other eye, and you will see that your finger is no longer lined up with my nose. And if you keep everything quite still and flick your eyes around like that, you will see your finger apparently flashing to and fro. And the reason for that is that when you use the second eye, you're looking at your finger from a slightly different direction, because your eyes obviously are not in the same place. Now, if you can measure the angle by which your finger appears to have moved compared with the background, which is my face, and you know the distance between your eyes, if you think about it, you'll realize that you've got a triangle. And the third angle, the one at your nose, must be a right angle. And so if you can measure that angle by which your finger appears to flick around, you've got every method for measuring that particular triangle and working out the distance between your finger and your nose. Now, it's much the same thing when we come to measure the distances of the stars. But of course, you want a very long baseline, a great deal longer than the distance between your eyes. And what we do is to use the Earth's orbit, because the Earth goes around the sun, as we know, and in 6 months it travels from one side of the sun to the other. And I'm going to peg that out on the cricket field using the boys as stars. Now, there we have our setup. We have what looks like a collection of boys roughly at the same distance from us. We know that Paul is in fact nearer to the camera, and when we start to move the camera, Paul will swing, apparently, against the background. Not because he's really moving, but because the camera is. In other words, he's going to show parallax.
By measuring the position of the stars at different times of the year, astronomers could use parallax to work out their distances. The problem is that there are 300 billion stars in our galaxy alone. So many, in fact, that we still haven't seen most of them, let alone worked out how far away they are. But now, that's changing. In 2013, the European Space Agency launched the Gaia Space Telescope. Gaia is a spectacular star-scanning machine. It allows us to measure a star's brightness and colour with startling accuracy. That allows us to work out what the star is made of and how it's moving.
But that's not all. Gaia is so finely engineered that it can measure the precise distance of over 1.5 billion stars.
Project scientist Jerry Gilmore introduced the spectacular results.
So, Jerry, you've been working on this project for a long time.
Well, yes, I was one of the original proposers of this mission, which was 25 years ago.
Ooh.
I'm older than I look. Yeah, it's the first time ever we've had a really genuine three-dimensional view of our universe. Mankind's been looking for this for millennia. Now we've done it and released data on about 1.5 billion stars with distances for 1.3 billion, colours, positions and motions as well. So it is a complete transformation. It is a once in a lifetime of mankind event.
It sounds fantastic. So can we see this data?
Well, here's a picture. So there it is projected on the sky, but you can fly through that. Like you're on a starship.
Yeah, like on the Enterprise. These images show the precise three-dimensional positions of just some of the 1.3 billion stars Gaia has surveyed. But this revolutionary space telescope also determines their speed and direction of travel.
So this is an image that looks like it's a two-dimensional image of the sky. So we zoom in, see this is the inner regions of the Milky Way now.
Southern I can see movement, it's
and
shimmering.
Everything's moving, that's right.
It's like a shimmer.
You've got to be a bit careful looking at things like this, you get seasick.
The image shimmers because the stars it shows aren't static, but moving over time. this is a fantastic picture, but what more does it tell us? What does it tell us about the galaxy we live in?
The motions are the key information that allows us to do science. So when you've got a position and a speed of something, then you can work out where it came from.
It's precisely this skill which has allowed Gaia to reveal something completely unexpected. We used to think that all stars were found in galaxies, but Gaia is helping us find new objects which defy this rule. Hypervelocity stars. And I met with Wyn Evans to learn more. Well, thank you for talking to us. Let's get some geography here. When we talk about the Milky Way, what components do we have to think about?
So the Milky Way has a thin disk of stars and then a central bulge of stars. And surrounding this thin disk and bulge is a much more diffuse halo of stars.
Sort of just scattered around and about like this.
Like raisins in a currant bun.
Right.
And about 50 kiloparsecs away from the center of the Milky Way is the largest satellite galaxy. It's a dwarf galaxy, but still quite big, called the Large Magellanic Cloud. Let's put it here.
Yeah, 50 kiloparsecs, so that's 150,000 light years, something like that. It's here that Gaia has found a particularly significant star and traced its journey back to reveal startling new information about our largest satellite galaxy.
Perhaps one of the most remarkable early results concerns the hypervelocity stars. And these are stars that are moving very, very fast. One of the most interesting, which is called HVS3, has been traced back to the very center of the Large Magellanic Cloud.
Where exactly is HVS3, this runaway star?
It's about twice as far as we are from the galactic center. It's somewhere down here. And remarkably, it was ejected at about 800 kilometers a second, a huge speed. And this can only be caused by interaction with a supermassive black hole at the very center of the Large Magellanic Cloud.
And that's exciting because I don't think we knew that the Large Magellanic Cloud had a black hole at its center.
That's completely correct. We didn't really know the origin of many of these hypervelocity stars. Now, for the first time, we have traced one back to the center of the LMC.
So it really has moved a long way from the LMC. What will happen to it in the end?
It will hurtle out of the galaxy. It will be a wanderer in space between the galaxies.
Hypervelocity stars might hurtle between the galaxies, but for humankind, interstellar travel is not so simple. The nearest star, Proxima Centauri, light years away with its own orbiting planet. If humans ever escape the solar system, it's surely the first place that we'd head for. But if it takes light more than 4 years to reach Proxima Centauri, then what chance do we have? For years, science fiction made travelling between the stars look easy. But in reality, it's always seemed like an impossible dream. Until now. In 2016, Jim Al-Khalili investigated the technology that might be about to make interstellar voyages possible.
For decades, centuries even, we've been wondering what kind of vast engines will be needed to carry us to the stars.
There's one simple, overwhelming problem when it comes to travelling across interstellar space. As Douglas Adams once said, space is big, really big.
And so far, we've only been able to explore the tiniest fraction of it. The craft that we've sent furthest into space is Voyager 1. Launched in 1977, it's escaped the solar system and has started the journey through interstellar space. But it has a very, very long way to go to get as far as Proxima Centauri. Any practical mission to the stars would need to get there in a reasonable amount of time, say 20 years. But that means going incredibly fast.
The distance between Earth and Proxima Centauri is just under 4.25 light years. Now, that works out at roughly 40 trillion kilometres, or 4 times 10 to the 13. Now, in order to cover this vast distance in 20 years, a spacecraft would have to travel at 20% the speed of light.
Accelerating a spacecraft to the speeds needed to reach the stars would require much more energy than you could ever produce with a conventional rocket. It would need a completely new type of propulsion system. There's another suggestion. In April, Stephen Hawking and internet billionaire Yuri Milner announced that they were putting up $100 million to develop a new interstellar project called Breakthrough Starshot.
For the first time in human history, we can do more than just gaze at the stars. We can actually reach them.
There are two key features to this new system. The first is that the spacecraft won't be carrying its own engines. Instead, it'll have a sail that is propelled by the force of light.
Released from a launcher in orbit, the spacecraft will be accelerated by the second new concept, a vast array of lasers fired from Earth. Theoretically, the planned 100-gigawatt laser, that's about the same power output as 100 nuclear power stations, could accelerate a spacecraft to nearly a quarter of the speed of light in about 2 minutes.
It would reach Mars in just half an hour. It would overtake Voyager in about 4 days, and it will get to Proxima Centauri in a little over 20 years.
There's only one problem. To reach those speeds, the spacecraft will have to be incredibly light, probably weighing no more than 1 gram. It's not exactly the Starship Enterprise, but what could you achieve with a 1-gram spacecraft? I called up Harvard cosmologist Avi Loeb, one of the scientists behind the project, to find out more.
Avi, this is a hugely ambitious project. Do you really think it's possible?
Yes, we hope that we can achieve the goals of this very ambitious project within the lifetime of our generation.
You know, how much science can you do with a 1-gram payload?
Fortunately, these days we can pack a lot of smart electronics into a single gram. If you look at a cell phone and strip it from the protective case and strip it from the human interface, you are left roughly with a gram. And that includes a camera, a communication device, a navigation, all of the ingredients we need in the Starshot spacecraft.
And what's the time scale for the project?
We hope to reach the final design within about 20 to 30 years from now. Following that, we hope to launch the spacecrafts, and it will take them about 20 years to reach Alpha Centauri and another 4 years for the signal from them to reach us. And so altogether, we hope to get those signals while we are still alive.
I'm the same age as you, so I just hope we're both around to see this project completed and successful in our lifetime. I wish you the very best of luck.
It's astonishing to think how far we've come since the days of the first telescopes, decoding the light of the stars to uncover how they work, where they are, and where they're going. And yet, there are even bigger questions left to answer. Where do stars come from? What happens to them when they die? The answers involve some of the most dramatic events in the history of our universe, events to which we owe our very existence. But uncovering those answers wasn't easy.
The stars, obviously, come from somewhere. What we'd like to do is to find out just how stars are born, how they die, and how they evolve. But that is by no means easy. And this is why I'm delighted to introduce back to the sky at night Heather Cooper. Welcome back again, Heather.
Thank you.
I think you'll agree with me that the sky is anything but peaceful.
Oh, it's churning away like anything. Stars are being born, they're living and dying. The trouble is they last for such a long time. It's very difficult to follow something that's lasting for 10,000 million years. So we really are in a bit of a problem with our short lifetimes of our own.
To get around the problem, astronomers had to find a new approach.
stretch your imaginations very considerably and imagine that I represent an evolving star.
Which Patrick memorably demonstrated in 1978.
I want to begin this programme by showing you a few photographs. First of all, here's a picture of a small boy. Quite an ordinary small boy, I think you'll agree. Here's a teenager. And here's a picture of a last war Air Force navigator. Well, those pictures are, of course, all of me at various stages in my career. But, of course, although I've aged very much in the last 55 years, I don't do it sufficiently quickly for you to notice anything just by looking at me for a few minutes. Now, you may wonder why I've been showing you pictures of myself. The answer is that there is a link here with the stars, because you just cannot watch a star and see it change as it grows older. So if we want to find out anything about the evolution or the life histories of the stars, we've got to adopt a rather different method. What we have to do is to look at stars which are rather obviously at different stages in their careers and work out which is the older, which is the younger, and try and get some kind of a picture from that.
This method allowed astronomers to finally piece together a star's eventful life cycle, starting with the moment when it's first born. And the best place to look for infant stars is in a stellar nursery.
There are nebulae, clouds of gas and dust. Here's one in the Sword of Orion, more than 1,500 light-years away. And that is a stellar nursery. Inside that, new stars are being created, and about 5,000 million years ago, our sun was born inside a nebula in just that way.
Nebulae are vast, swirling clouds of gas and dust, stretching hundreds of light-years across. But don't let their serene appearance fool you, because inside them, a spectacular process is underway. At the heart of these molecular clouds, gas and dust pull together under gravity until the cloud collapses under its own weight. The pressure and the temperature increase until a thermonuclear reaction is triggered and a new star begins to shine. This energizes the leftover gas around it, so the clouds of the nebula start to glow. Each element shines a different color, creating rainbows of oxygen, helium, and hydrogen in some of the most beautiful sights in the entire cosmos. These stellar nurseries are breathtakingly beautiful, but they pose a conundrum. To form stars, these gas clouds have to cool and then collapse, something they can only do when molecules of hydrogen are present. The trouble is, it's hard to form molecular hydrogen in space, a puzzle investigated by chemists Andrea Sella and Steve Price in 2014.
Doing chemistry on Earth is very easy, but in nebula, we've got very low pressures, so the H atoms don't encounter each other very often at all, and it's very cold, so they don't hit each other very hard, but also they can fall apart very easily. We need something to actually bring the H atoms together to help them react and actually form that H2 molecule.
Luckily, nebulae aren't just vast clouds of gas. They're also full of microscopic dust particles. And it's these dust particles that are key to forming new molecules.
So what's the role of these dust grains?
Well, the dust grains allow us to bring the atoms of hydrogen together to form H2. The atoms stick on the surface of the dust grains, they run around and find each other. Without the dust grain, the atoms wouldn't really encounter each other for long enough to make H2. So it's vital in bringing them together and making the reaction happen.
What do they look like?
We think the dust is rough, and here's a picture of some simulated dust grains that people have made in the laboratory, and you can see they're nothing like your nice flat plateau
horrible.
of carbon. I think they look
It
quite
looks
pretty.
like cauliflower.
But what you can see straight away is its sort of textured and fluffy surface is actually perhaps important for trapping molecules on the surface of various other things. So the structure of the dust is really quite important.
Once the molecular clouds collapse and the star finally ignites, it begins an extraordinary life cycle, one which will eventually change everything. But just as individual stars are different, so their lives and deaths are too, and these differences are governed by one thing above all else:
The whole career of a star does depend upon how much mass it originally has.
There are two paths a star can take. Both are remarkable in their own way and result in some strange and surprising phenomena. The first journey is that of a normal star, like our Sun.
Well, we've taken the story some way. These stars we're talking about now are hot and energetic because they're using up fuel, which is mainly hydrogen, and that fuel is not going to last indefinitely. So a star is going to change when it starts to run short of fuel, and that's the next stage in the story.
That's right. Now, stars are a bit like hydrogen bombs, but they're so big and they're so massive they don't actually blow up. And gradually they do run out of fuel. They can only process that fuel very, very deep inside them where the temperatures and pressures are very, very high. But there comes a stage, as you say, when they run out of fuel. And oddly enough, when a star runs out of fuel, it swells up and becomes much cooler and therefore redder, and it turns into a red giant.
Such as Betelgeuse is now. The diameter is over 200 million miles, and that is greater than the path of the Earth around the Sun, so it really is huge.
That's right. But of course, the way it got there is very interesting. It's not certain how, but the best spy model at the moment is that when Betelgeuse ran out of fuel, its centre collapsed in on itself, and when you collapse gas, you actually compress it and make it hotter. And as the core heats up, and of course it's a dead core, it can't actually process any more fuel, it heats up the layers of the star further out, and that in turn causes a shell of burning. It's a hydrogen to helium burning, and the outer layers just billow out in this kind of red giant shape. So it really is an enormous thing. And as you say, they don't last forever. It seems that after all this wobbling about like a celestial blancmange, Betelgeuse will eventually jettison those layers into space.
These old stars lose their gaseous surround, and we're left with the old stars themselves, and that comes right on to the idea of a white dwarf star.
That's right. Now, these stars are actually the compressed remnants of the old star. They're the central core, and they are just so collapsed in on themselves that if you went there with your trusty teaspoon and picked up 1 teaspoonful, the matter's so compressed it would weigh a ton, which is quite incredible. And that's very, very nearly the end of a star like the Sun, because the white dwarf has got no fuel left, and all it can do is just sit there and leak away its heat into space, and eventually it'll end up as a cold black globe.
Well, that's the eventual fate of the Sun, although I'm afraid that the Earth won't be there because the Earth can hardly survive the red giant stage.
Oh, but there's no panic because it's not going to happen for 5,000 million years.
When the Sun dies, it will bring our solar system's story to an end. That sounds pretty devastating to you or to me, but actually, it's not that spectacular, because stars much more massive than the Sun have a very different and much more dramatic fate in store. A star that large won't just collapse, it will go out with a bang.
When it runs out of fuel, it can no longer resist its own gravity, and it collapses and rebounds in a massive explosion. It releases as much energy in that single instant as our Sun will release in its entire lifetime. It suddenly becomes brighter than tens of billions of ordinary stars. This picture shows a supernova almost outshining an entire galaxy. Supernovae aren't rare. In fact, it's thought that throughout the universe, 10 occur every second. But most of these are too distant to notice, and they can only be picked up by the most powerful telescopes. But sometimes, every few hundred years, a supernova occurs within our own galaxy. When the light from this explosion reached Earth in 1054, it was as if a new star suddenly appeared in the night sky. It blazed as bright as the moon for 2 years before fading. But it made a real impression on the people of the time, and a new star was recorded by the Chinese, the Japanese, and also in the Middle East.
These rock paintings in the American Southwest are thought to show the position where the supernova appeared in the sky. Our ancestors were captivated by the rare sight of supernovae visible from Earth, but little did they suspect that these events were more profoundly significant than they ever could have imagined. because something is created at the heart of a supernova which holds the answer to one of humankind's most enduring and important questions. Where do we come from?
The one inescapable fact, at least I think it is that you and me and your television set and the kitchen sink and Aunt Emily, they actually exist. So the matter making up ourselves must have come from somewhere.
When the universe began, all that existed were the lightest elements of all: hydrogen, helium, and a sprinkling of lithium. But here on Earth, we see much more than just hydrogen or helium. Our world, the trees, the telescopes, even my body, are made out of a rich variety of elements. So where did they come from? Supernovae are some of the most powerful explosions that we know. The conditions inside them are so intense that atoms fuse together to create brand new chemical elements. Everything from the oxygen we breathe to the iron in our blood was forged in the heart of a supernova. And that's just the beginning. As the supernova's shockwave moves outwards like an inflating bubble, it heats the gas that it passes. And this causes brand new stars to burst into life. A new generation rising from the remains of those that came before them. So as well as forging the elements and spreading them throughout the universe, dying stars are also responsible for bringing their life cycle full circle. So the whole process can begin again. Stars are the agents of creation. I find it remarkable that the atoms that make up me, you, and everything around us were forged billions of years ago in massive stellar explosions. All part of a cyclical process that's been going on for billions of years and which will continue for billions more. It's humbling to think how far we've come since the birth of astronomy, when we had nothing but our own eyes with which to observe the stars in the night sky.
I hope you've enjoyed our journey. It's taken us round the world in our pursuit of knowledge. Today, we are probing out to the depths of the universe, and every year we are solving new problems, though each problem we solve seems to raise a whole host of others.
With each breakthrough, we've realised that the stars are more dynamic and more surprising than we ever would have thought. So next time you look up at the night sky, don't write the stars off as mere pretty points of light, because hidden in that light is the entire story of the universe.